Hey there, chemists. In this unit, we're going to look at what's called thermochemistry, which is how we relate heat and energy to chemical processes. I'm going to dive right in and show you two new equations we use to calculate the amount of heat related to anything that has a temperature change or a phase change. So see, these are just physical changes today. We're going to use this moving forward and talk about how we get it for chemical changes, but today it's just for physical changes. We use the letter Q to talk about heat, and if there's a temperature change, the equation is based on the mass of a substance, so m times the specific heat of that substance, that's based on what the substance is, times the change in temperature. So how much of it do we have, what is it, and how much hotter or colder does it get? That's what dictates the amount of heat related to a temperature change. M is mass, and C is the specific heat. Which different substances have different specific heats. You can see a couple down here in the lower right. Water as a liquid has a notoriously high specific heat, so it takes a lot of energy to heat up a quantity of liquid water. Things like metals have notoriously low specific heats. It doesn't take a lot of energy to change the temperature of a metal for the most part compared to something like liquid water. So that's what we do for temperature changes. What about phase changes? Well, we also use the letter Q, and it's only based on how much of the substance you have times what the substance is, and we use this delta H symbol to mean the latent heat. That's just how much energy it is to change the phase of that substance. In the lower left, we have a chart again, just for solid and liquid water, and you can see the latent heat is in energy per amount. It takes a lot more energy to boil liquid water than it does to melt solid ice, for example. Different substances have different specific heats and different latent heats. We can also sometimes do this in terms of not mass, but moles. So we might see an equation where it's the latent heat per mole, and then you use N instead of M. Conceptually, it's the same thing. It's based on the amount of substance times a property that's based on what the substance is. So delta H is the latent heat. Now, speaking of phase changes, everybody should be familiar with the names given to the phase changes. If you go from solid to liquid, that's melting. If you go from liquid to solid, that's freezing or solidification. Liquid to gas, that's boiling. Gas to liquid is condensation, the opposite. And then sometimes you see solids turning directly into gases because phase changes depend on pressure as well as temperature and the identity of the substance. Solid to gas directly is called sublimation, and the reverse of that is deposition. You should just know those words and what phase changes they represent. Here is an example of visualizing the combination of a temperature change and a phase change, a temperature change and a phase change. This is a plot of temperature versus essentially energy or heat, which usually correlates with time. You can imagine having a solid sample of something like ice and then melting it to turn into liquid water and then boiling it to turn into gaseous steam. And you can see in the particle diagrams what the particle arrangement looks like. Very ordered and dense in the solid phase, still dense in the liquid phase, but more randomized, and then much more spread out in the gaseous phase. That's true for all substances. And these plateaus, which are labeled B and D, are the phase changes. Notice the temperature stays constant for a phase change. So when something melts or when something boils, the temperature reaches a plateau. As long as it's a single substance, until you get to another temperature change. So now let's put these together, both temperature changes and phase changes, and talk about the heat related to some physical changes. The first one says we have a sample of iron with a given specific heat at some temperature. We mix it with a sample of copper, which has its own specific heat at a different temperature. What's the final temperature when the two metals are put together? I always find it helpful to visualize what's being talked about in words. So we have a sample of iron with some mass and some initial temperature. We have a sample of copper with some initial mass, and we're going to mix the two. Well, the conservation of energy says that the heat lost by one will be gained by the other. So Q plus Q is equal to 0. And that's an equation we're going to use a lot in these problems and moving forward when we talk about chemical changes as well. But here we're still just talking about physical changes. So the heat of the system, we'll say Qsys, plus the heat related to the surroundings, Q surroundings, is equal to 0. What's lost is what's gained in magnitude. Now we're only talking about temperature changes. They want the final temperature after you smash these two metal samples together, each with their own initial temperatures and masses and specific heats. So we're going to use this first equation, the MC delta T equation, for both of these. So there's an MC delta T for the system and an MC delta T for the surroundings, and they're equal to 0. In this case, it doesn't really matter which one is the system and the surroundings. They're just mashed together, but one is one and one is the other. So let's call the iron the system. It has a mass of 20. It has a specific heat of 0.45 joules per gram degree Celsius. Now the delta T is the unknown final temperature that we're looking for minus the initial. So T minus the initial temperature of 200 degrees. Delta T is always final minus initial, always. Sometimes it's a positive number, sometimes it's a negative number, but it's always final minus initial. So what's the MC delta T for the copper? Well, there's 50 grams of copper. The specific heat is 0.39 joule per gram degree Celsius, and the delta T is T minus 100. And just conceptually, if we set those equal to 0, we can now solve for the math, but let's do a concept check. What should the final temperature be? Well, it's got to be between 200 and 100. It can't be lower than 100 or higher than 200. And we can think about how much of each substance we have and what their respective specific heats are. Does it make sense where it meets in the middle? Not halfway, but probably closer to one than the other. Anyway, let's distribute all of this algebra and solve for the T. The first one, if we expand, becomes 9T minus 1800 plus 19.5T, and then minus 1950, set equal to 0. There's the expansion of the first term, and there's the expansion of the second term. Now let's combine like terms. We get 28.5T. Let's move these whole numbers to the other side, equals to 3750. Divide both sides by 28.5. We should get a T of 132, and that's in degrees Celsius because we were in degrees Celsius originally. And that makes sense. It's between 100 and 200, so it should be between them. And you'll notice it's actually closer to the copper sample, right? There's more of the copper, so it's probably going to heat up less than the iron cools down. Their specific heats are actually pretty close. They're not identical, but the mass turns out to dictate where this thing ends at the end. Okay, so using that as an example, I want you to hit pause and try the second one right next to it. Here we have two liquids mixed together. Again, visualize what's going on. See if you can figure out the final temperature of the mixture, and then unpause and come back and see how you did. Okay, let's see how you did. So here we have two liquids. They don't even say what they are. But again, if I visualize, I have a sample of liquid that's 30 grams in the beginning, mixed with another batch of the same liquid. This one's 50 grams, and we simply mix them together. So this is another Q system plus Q surroundings is equal to 0. We're only talking temperature changes. It's all liquid in the end, so it's MCAT plus MCAT is equal to 0. We know the mass of each substance. We're solving effectively for the final temperature, which is buried in the delta T of each, but we don't know the specific heat of each. Well, let's fill those in. It's going to be 30 grams of some C value for the liquid times T minus 280 for the smaller batch, plus 50 grams times C, the specific heat, times T minus 330 for the other larger liquid, and set equal to 0. Now this looks like we have two unknowns and only one equation, but if you think about it, it's the same liquid, so C is the same, and we can actually cancel that out from both terms if we divide everything by C. So there we don't need to know what the C is. We can expand these. The first part becomes 30T minus 8400. The second part becomes 50T minus 1650. That's all set to 0. Let's combine like terms. You get 80T is equal to 2490, and T is 311, and it's in Kelvin this time because these were initially in Kelvin in the beginning. I never needed to convert, because a delta T in degrees Celsius is the same as a delta T in Kelvin. So you can keep your units of Celsius into Celsius or Kelvin into Kelvin. And just a quick concept check, does this make sense? Well, first of all, yeah, it's in between 280 and 330, and it's closer to the temperature of the one that there was more of. So it makes sense that these would equilibrate at the end and reach a temperature that's closer to the one that's more significant. Okay, so let's try one more. This time we're gonna loop in a phase change as well as a temperature change. Number 3 says we have a sample of ice at 0 with 250 grams of water that's very hot, 90 degrees Celsius. And what's the final temperature of everything, assuming it's all liquefied at the end? So first let's visualize. We've got a chunk of ice that's 40 grams and initially at 0 degrees Celsius. And then we've got a sample of water that's 250 grams and 90 degrees Celsius. And we're gonna mix the two, and it's all liquid water at the end. So we're obviously gonna melt this ice, and then we're gonna heat up its temperature as well. And simultaneously, we're gonna cool down the temperature of this liquid water. So we actually have 3 Q terms this time. We're gonna have a Q for the melting the ice, a Q for the warming up the melted ice, which is now a liquid. What used to be a solid has melted and now it's gonna heat up. And then we're gonna cool down the liquid water. So we have Q plus Q plus Q is equal to 0. The sum of the Q's is what's equal to 0 in each of these cases. Now the melting ice is our phase change. First time we're using that other equation. So 40 grams times the delta H, the latent heat, which is given down here for solid ice. Now it's melted, we're gonna warm it up. So it's still 40 grams. The specific heat of liquid water is 4.18. That's in the lower right here. Liquid water has a specific heat of 4.18. And then we're gonna cool down this hot water. That's 250 grams, and then a specific heat of 4.18. And the delta T is T minus 90. I neglected to talk about this T. The delta T for the melting ice is the final temperature we're solving for minus the initial. Here we're cooling down this hot water that's initially 90 and at a final T of here. Remember, delta T is always final minus initial every time. So we have one equation and one unknown. Let's expand everything and solve for T. So we've got 13,360 for this first term. This second term becomes 167.2 T. And this third term becomes 1045 T minus 94,050. Let's combine like terms and get 1212.2 T is equal to, moving everything to the other side, 80,690. Divide both sides by 1212.2 and you get T is 67 Celsius. Again, concept check, does it make sense? Well, we've got a chunk of ice at 0 and a hot batch of water at 90 Celsius. Yeah, this is gonna cool down the water a little bit and heat up that sample of 40 grams to the same temperature. Makes sense that it's in between 0 and 90 and closer to the 90. So when we have a phase change, we just have to add that in to the other Q terms. You could have multiple Qs that add up to 0, in this case, that combine the delta T changes and the phase changes as well. Hit pause one last time and try the last question, and then come back and check to see how you did. Okay, let's see how you did. Last one, we've got a sample of copper. It's heated from 12.8 to 63.1. How much heat is gained? This is actually the easiest question on this lesson. It's just one process. They just want to know the heat. So this is just calculating Q. It's only a temperature change, so it's MC delta T. We know the mass, 25.4. We know the specific heat, it's copper, so that's 0.39. And the delta T is always final minus initial. So 63.1 minus 12.8. You just do the math and you get 498 joules. Notice that Q is a positive number, so this is absorbing energy. We'll say that this is an endothermic case because energy is positive, it's being absorbed. That makes sense to heat up a sample from a cold temperature to a hotter temperature. Okay, so in this lesson, we looked at how to calculate things related to energy changes, specifically heat, namely for phase changes, temperature changes and phase changes. There's 2 new equations that we use today, and the principle of the sum of the heats is equal to 0 is the theme when you're combining things or just calculating the value of heat for each one. In the next lesson, we'll look at how we apply this to chemical changes and then combine the two. Thanks for watching.